Let's look at the Chapter 11 review questions. Question 1. A chi-square goodness of fit test is used to test whether a 0 to 9 spinner is fair. That is, the outcomes are all equally likely. The spinner is spun 100 times, and the results are recorded. The degrees of freedom for the test will be what? Now in this case, what they are doing is the goodness of fit test. Remember, the degrees of freedom for the goodness of fit is the number of categories minus 1. So in this case, the number of categories, there are 10 different options for this, so 10 minus 1 is going to be 9 degrees of freedom. Question 2. Recent revenue shortfalls in a Midwestern state led to a reduction in the state budget for higher education. To offset the reduction, the largest state university proposed a 25% increase. It was determined that such an increase was needed simply to compensate for the lost support from the state. Separate random samples of 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors from the university were asked whether or not they were strongly opposed to the increase, given that it was the minimum increase necessary to maintain a university's budget at current levels. The results are given in the following table. So we have here a contingency table based on the year they were in and then their response. Question 2. Which hypothesis would be appropriate for performing a chi-square test? This basically comes down to, is this going to be a chi-square goodness of fit, independence, or test of homogeneity? If this was a test for goodness of fit, there would have been one sample. The key to this problem is they were separate random samples. So in this case, we have 4 different samples. The test for homogeneity is when you have 2 or more samples and 1 variable. So in this case, we have 4 samples, and the 1 variable is if you were opposed to this. So this is going to be the test for homogeneity. Based on that, you should recall what your hypothesis would state for a test of homogeneity. In that case, what you would say, your H sub O for that would be that there is no difference in the distribution of treatments, whereas your H sub A is that there is a difference in your distribution of treatments. The hypothesis that's stated here that best meets this requirement is going to be letter C, which says, the null hypothesis is the distribution of student opinion about proposed tuition is the same. That's our null. The alternative is the distribution is different for at least 2 of the 4 years. Now, why do the other ones not work? Letter A, the null hypothesis, is that the closer students get to graduation, the less likely opposed. This is just a conclusion someone's trying to make. It doesn't even make sense for that one. For B, the null hypothesis is that the mean number of students is strongly opposed. Chi-square is nothing about the means. Chi-square is about the proportions. So it cannot be letter B. Letter D, the null hypothesis is that year in school and student opinion about the tuition increases in the sample are independent. This is the chi-square test for independence, which we are not dealing with. We know it's a test of homogeneity. And then E, the null hypothesis is that there is an association. If this was a test of association, your null hypothesis would always start off that there is no association. So even if this were the case, this hypothesis is stated incorrectly for the test of association. Question 3 is an extension of that scenario. The conditions for carrying out the chi-square tests in that exercise are this. 1, that separate random samples from the population of interest. 2, the expected counts are large enough. And 3, the samples themselves and the individual observations in each sample are independent. Which of the conditions are satisfied in this case? If you check it, they already did talk about that they took random samples of all 4 different class types, so that's good. To check your expected counts, because this is a test of homogeneity, what you'd have to do, remember, to find your expected counts is you're going to have to do the row times the column, and you're going to divide by the total for all of the cells in the table. If you do that, you will find out that all of the expected counts are going to be greater than or equal to 5. Just so you see how one of them is checked, what if we look at the expected counts of freshmen saying yes? So what we would do is the row times the column. And in this case, the row for yes, there's 122 responses. the column total is 50, and then we would just divide by the total in this case, which is going to be 200. If you do that, you're going to get 30.5, which is greater than 5. You're going to want to check all of the other 7 cells in there and make sure they are greater than 5. Now, if you don't want to do this by hand, you could actually make a matrix in the calculator and input the responses. You could run the test of homogeneity, and then after that, you could go back and look at the second matrix and actually read the expected counts. Keep in mind, if you were doing a free response question with this, you have to write down every single expected count. In that case, what I would do is run the test in the calculator and just copy the expected counts from matrix letter B from the calculator itself. Now, the third condition is the independence. And in this case, we can assume that there are at least 500 students from each of the classes that we can choose from. So based on that, letter E is our best option. All conditions have been met. As a good review, it's important to make note that the test of independence and association and the test for homogeneity are the ones where you end up using the expected count formula of this one, which is a little bit more involved. So keep that in mind and realize it's separate and done differently than finding expected counts for goodness of fit test. Question 4. A random sample of traffic tickets given to motorists in a large city is examined. The tickets are classified according to the race of the driver. The results are summarized in this table below. So here we're seeing number of tickets and the race designation between that. The proportion of the city's population in each of the racial categories is also listed below. We wish to test H sub O, which is the racial distribution of traffic tickets in the city, is the same as the racial distribution of the city's population. Assume H sub O is true. The expected number of Hispanic drivers who would receive a ticket is what? Now, again, you want to think about, is this goodness of fit, independence or association, or homogeneity? This right here is going to be a test of goodness of fit. So to find the expected counts of goodness of fit, we are just going to realize we're talking here for the Hispanics, so this is what came out of the study. There are total, if you add up this table, 148 people. The population says there's 8%, so to find the expected count, let's just take 148 times the 8%, and that's going to get us an expected count of 11.84. Now be careful if this was a free response. Never ever round this number. This is a theoretical answer, so 11.84 is correct. Never round it up to 12 or down to 11. Continuing on with that scenario number 5, we compute the value of the chi-square statistic to be 6.58. Assuming the conditions for inference are met, the p-value of our test is what? Now, you don't need to know how to draw what chi-square looks like, but if you do reference your formula sheet, the chi-square statistic is actually tends to be skewed to the right of this nature. If they found that this statistic was the number 6.58, they want us to compute the p-value. So the p-value that we are going to be looking for is going to be this part of the tail. All you need to do is on your calculator, you can do the chi-square statistic. This is the CDF because it's a cumulative value. We just put 6.58. We're going to go up to 999. And the degrees of freedom for this is going to be how many categories we had minus 1. If you look back, remember we had 4 categories in terms of the response, so degrees of freedom would be 3. When you do this, the p-value is going to give you 0.0865. Now you also could run the goodness of fit test on this and it will kick out the p-value in there. That's another way to get this answer. Or you could use the chi-square statistic table, and if you use the chi-square table, you're going to realize that the answer is going to be somewhere in between 0.05 and 0.10. So you really don't have to use the calculator for this one. The response that they have given you is one where you could use the chi-square table on the formula sheet. I personally like to just use the calculator, but that's just my preference. Number 6 wraps up this data. The category that contributes the largest contribution to the chi-square statistic is what? What you want to do for this is actually run the goodness of fit test. And then at the end of the test, you're going to want to scroll and look at what the contribution values are. When we do that, what you're going to notice is for the white population is 1.88, the black population 1.3, Hispanic was 3.2, and then the other category was 0.178. You can determine it. Again, you're going to have to use your calculator to get that response. The one with the highest contribution clearly is going to be the Hispanic population. I will tell you the AP board says they will probably not make you find what the chi-square contributions are. However, they may give you the output, and from there you would have to read and interpret in your analysis what meets the requirement that they're looking for. Question 7 through 10 is referring to this setting here. All current carry wires produce electromagnetic or EM radiation, including the electrical wiring running into, through, and out of our homes. High-frequency EM radiation is thought to be a cause of cancer. The lower frequencies associated with household current are generally assumed to be harmless. To investigate this, researchers visited the addresses of a random sample of children who had died of some form of cancer, leukemia, lymphoma, or some other type, and classified the wiring configuration outside the dwelling as either high current configuration, which is HCC, or low current configuration, LCC. Here's the data. So what we're seeing here is there's 3 responses of the 2 different types of wires. Computer software was used to analyze the data. The output is given below. It includes the cell counts, some of the expected cell counts, and the value of the chi-square statistic. In the table, expected counts are printed below observed and are enclosed within parentheses. So our expected counts are right here in our parentheses. The observed counts are right above there. Again, chi-square statistic is right here. First question for number 7. The appropriate degrees of freedom for the chi-square statistic is what? Again, let's determine, is this goodness of fit, independence or association, or is it homogeneity? Goodness of fit is one sample in one variable. Well, in this case, there's 2 different variables that were actually looked at. It was just one sample, but the variable is the type of wiring and the kind of cancer if it existed. So it's not goodness of fit. Independence is one sample in 2 variables. So again, it says here they took one sample out there in our write-up, which is going to be right there. So it is one sample, and it's 2 variables. So that would be, this is either independence or association. It would not be homogeneity, because homogeneity is 2 or more samples in one variable. This was just one sample. So degrees of freedom for that, to calculate it, it's going to be the number of rows minus 1 times the number of columns minus 1. So in this case, we have 2 rows minus 1, and we have 3 columns minus 1. So our degrees of freedom is going to be 2. Question 8, the expected count of cases with lymphoma in homes with HCC is what? So if we go up to the table and we find lymphoma with HCC, is this observed amount? So remember, we've already talked about this. To find the expected count, it's going to be the row total times the column total over the total of all of the data in this table. So that's going to be 79 times 31 over 215. And that's going to give us this value right here, or letter C. Question 9, which of the following may we conclude based on the test results? If you look back at the table, we saw that the chi-square value was 0.435. So again, remember the distribution of chi-square is something like this. They want us to find this value, or the probability of this happening. So we're just going to do a chi-square CDF in the calculator at 0.435 of 999, and our degrees of freedom we already know is 2. If you do that, it's going to kick back a p-value of 0.804. Remember, the definition of p-value is the probability that our particular sample happened given the fact that H sub O is true. Now, what I think is important is they never ask it, but I think you need to understand what the initial hypothesis was for this. Because this was a test of either, we could say independence or association, If we said, if we look at the answers, we're going to see a lot of them are using association. So let's write it as that. H sub O for that would say that there is no association, but H sub A would say that there is an association. So this p-value again reflects the probability of our statistic given the fact that there would be no association. How do we evaluate it? We would just say here that the p is less than alpha. Again, we're going to default alpha at 0.05. It's the standard value to use. Because p is less than alpha, we fail to reject H sub O, and we cannot conclude H sub A. So we cannot conclude that there is an association between this. The answer here that is going to reflect that is going to be letter D, which says there is not much evidence of an association between wiring configuration and the type of carrier that caused in this study. Again, my recommendation for this is they don't ever ask it. I always write down what I think the hypothesis would be like, and that helps me visualize what the conclusion would actually be. Some of the things to point out on here, for example, C, this option for C is the most common type of cancer. That's not a conclusion we would make based off the test. That just might be an observation that we're seeing from the data. Letter B, HCC either causes cancer directly or is a majoring factor. We clearly can't say that. Letter A, there is strong evidence. The p-value is much too large to say that. There is definitely not strong evidence. E, there is weak evidence. You don't even know if there's weak evidence. I mean, we don't know if this is considered weak or not good at all, so that's really pushing it. D here is clearly the best response. Number 10, a type 1 error would occur if we conclude what? You're going to notice I did jot down the hypotheses here again. So you have to remember type 1 and type 2. Type 1 is we reject H sub O and we conclude H sub A when we should not have. Remember type 2, we fail to reject H sub O and we cannot conclude H sub A when we should have. So keeping those two straight. So type 1, we rejected H sub O and we concluded H sub A and we should not have. So if we do that, we would have concluded H sub A, which says there is an association. Type 1 error would conclude what in this case? Well, if you look at it, D is going to be the correct answer. We would conclude there is an association between the type of wiring when there actually is no association. So that is going to be the type 1 error. Let's go back to the other options. Letter A, HCC wiring causes cancer. First of all, one thing to really highlight here, you can never say a cause and effect. Remember, a cause and effect implications are only if an experiment was imposed. There was no treatment, there was no experiment. You never can say that if it's an observational study. Letter B, HCC wiring didn't cause cancer. Again, they're using this cause thing. There was no treatment? We don't know. Letter C, there is no association between the type of wiring. Again, by default, we know this would not be the correct statement for type 1. This would be more of a type 2. And then letter E, the type of wiring and form of cancer have a positive correlation when they actually don't. You have to be really careful with letter E because when they say they actually don't have a positive correlation means they're coming back and they're concluding H sub O. You can never, ever conclude the null hypothesis. So this is clearly an error because of that. Switching over to the free response. A large distributor of gasoline claims that 60% of all cars stopping at their service stations choose regular unleaded gas, and that Premium and Supreme are each selected 20% of the time. To investigate this claim, researchers collected data from a random sample of drivers who put gas in their vehicles at the distributor's service station in a large city. The results were as followed. Carry out a significance test of the distributor's claim. Use a 5% significance. So again, first question, goodness of fit, independence/association, or homogeneity. This is clearly one sample and one variable that was measured, so this is going to be a test of goodness of fit. So what I would first state, for my state, it's a goodness of fit test, a chi-square, and I'll actually put that, chi-square, goodness of fit test. That is basically my statement. My plan, we're going to do random, independence, and normalcy. So for random, it says right here there was a random sample, so you should write down that there was a random sample. I'm going to jump into independence on this one. If we tally this table up, by the way, there are 400 different samples that were taken. So for the independence test, we have to assume that there were at least 4,000 people getting gas. So write down that there are at least 4,000 people getting gas is a fair assumption. Now we need to make sure expected counts. So to find our expected counts for this one, what we're going to do is remember the breakdown. They are thinking there's 60% here, 20, and 20. So to find the expected counts, because what we're given here are the observed counts, expected counts, if we take 400 times 60%, you get 240. This next one we get 80. The next we get 80. And we can just say expected counts are all greater than 5. Greater than or equal to 5. So we've met the chi-square distribution requirement for that, and they are large enough. Now the do portion, I would just put this data in your calculator, and what I would write down to give yourself credit for do is jot down the chi-square statistic. It's going to kick back at 13.15. You must list the degrees of freedom. There are 3 categories, regular, premium, and supreme. So remember, it's sample size, or number of categories minus 1, so it's 2. The p-value from the calculator kicked back at 0.00139. And that's all you need to list. Make sure you stated that's a chi-square goodness of fit test. I will tell you the AP board will make this suggestion. If you know it's chi-squared, but you're not sure if it's goodness of fit or homogeneity, the best way to kind of cover your butt on this is if you state the wrong test, you will lose some points. But if you're really not sure which one of the 3 it is, if you just say it's chi-squared, it's possible that they would give it to you and dock you fewer points for not using the wrong vocab word. All right, let's go to the conclusion. So for conclusion for this, our p-value is less than alpha. I'm going to write that down. Is less than 0.5. Because of that, we can reject H sub O. And we conclude H sub A. Again, make sure you have that in context. On here, I did not write down the hypothesis, so I was missing that. Let's get that part of our plan. What is the hypothesis? It's incredibly important. You do not want to forget that step like I did at the beginning. So let's make some room for that right here. The hypothesis for goodness of fit, because we have to use that to make our conclusion. H sub O versus H sub A. Our H sub O could be that there is no difference in gas distribution. In our H sub A, there is a difference in gas distribution. Again, I would recommend to actually put this hypothesis. I probably should have stated it before I did my conditions, but as long as it's on here, I am still okay. Now we can make our conclusions, which is about concluding. I have H sub O here, you guys. Careful with my writing. Concluding H sub A. We do need to say this in context. So what I would say is we reject H sub O and we conclude that there is a difference in the gas distribution at this gas station. Number 12, a study conducted in Charlotte, North Carolina tested the effectiveness of these 3 police responses to spouse abuse. First, advise and possible separate the couple. 2, issue a citation to the offender. 3, arrest the offender. Police officers are trained to recognize eligible cases. When presented with an eligible case, a police officer called the dispatcher, who would randomly assign one of the 3 available treatments to be administered. There were a total of 650 cases in the study. Each case was classified according to whether the abuser was subsequently arrested for 6 months to the original incident. So what we're seeing here is a contingency table of treatment and subsequent arrest record. Part A, explain the purpose of random assignment in the design of the study. This is basically a Chapter 4 review question, and the purpose of this is to ward off lurking variables. Remember, it is important to do the random assignment because the lurking variables in themselves, if lurking variables are too powerful, what happens is they actually can confound with the response, and they would change the response what would naturally happen. If you control for their lurking variables, then they can't confound, and in theory, they will not have an impact on the response variable that we're measuring. Part B, construct a well-labeled graph that is suitable for comparing the effectiveness of these treatments. Or in this case, the samples that we're seeing for here. Now, there's different graphs you could make. What comes to mind for me to do is to make maybe a stacked bar graph. If I were to do a stacked bar graph, what I would recommend is right here. I'm going to put the advice and separation for right here. I will put the citation happened, and I would put the arrest. And you should put the full word. Because we are comparing different totals, this should be a percentage that we're going to look at. When I do the percent, if I do it for all of those advice and separation, if we tally this up, this is going to give us a total of 212. So the percent for that, we will do, let's do no arrest. I will do my color of no arrest in yellow. So if I do 187 over 212 as a percent, we're at about an 80%. So I'm going to do this, and I'm sorry, I had 88%. So I'm just going to mark that as 88. And this is going to be 100% of the total, so I know to get back up to the 100%. I'm going to go ahead and do this one in the green. This is going to be my 100% level right there. And that is going to be my subsequent arrest. So we should make a key for this, though. Put on here, for me, the yellow is the no subsequent arrest, the green are subsequent arrests. If I complete this graph, I'm going to get the rest of my totals and do my percentages. And that's going to leave me at about 80% for this one here, so I'm going to go just a little bit lower, which means we're going to have the subsequent arrests a little bit higher for those with citations. And then if I do the 175 divided by 214 total, I'm at about at 82% for the arrests. I'm going to be a little bit higher on that one. Switch my color back. And then we're going to wrap it up and have this. So the stacked bar graph is nice. Again, we want to do it as percentages because our row and column totals are not the same. So you must do a percentage. And then you would add a key. Again, what does the green stand for and what does the yellow stand for your graph. Part C, we want to use these data to perform a hypothesis test that proportions are all equal, which is H sub O, where P is the true proportion of spouse abusers, like the ones in the study, who would be arrested again within 6 months after receiving treatment. State an appropriate alternative hypothesis. Well, if the null is that all the proportions are the same, we know our alternative hypothesis in this case would be H sub A, and we could just say that they are all different. You could actually just say there are some differences in the proportions. You could just list that out. You could do P1 is not equal to P2, maybe is not equal to P3 kind of thing. I personally prefer just to do the word so that there is some difference in the proportions. Or you could say, instead of some difference, there's at least one difference you could say instead too. So you could say, you know, at least one difference in the proportions. There are different ways of saying this or stating it mathematically. I think it's good to be exposed to all of them, but that's just more for multiple choice purposes. For a free response, they're going to accept any one of these types of responses for that. Now let's even talk about what test is this going to be. Is it goodness of fit, independence and association, or homogeneity? We clearly know it's not goodness of fit, so it's either between homogeneity or an association. What you want to be careful of here is there are 3 different treatments in this case. What that is there were 3 different samples going on in theory. So there's 3 samples, and the one variable of measurement was the arrest record that they had on that one. So 3 samples, 1 arrest, or 1 variable. So in this case, we are talking, this is a test of homogeneity. So when we look at Part D, it says this. Assume all the conditions for performing the test are met. It yields a chi-square of 5.063, which is a p-value of 0.0796. Interpret the p-value in context and what conclusion could be drawn. Again, if we look at the hypothesis stated in Part C, by the way, if you remember how your hypotheses are stated, this clearly is stated as the test of homogeneity. Okay, let's start by interpreting the p-value. Remember, definition of p-value is going to say the probability of this statistic happening, right, given the fact that H sub O is true. So if you know the standard default, you can actually put that in context. And here's what I would say. I'm not going to write it down, and I'll say it for p-value. I would say given that all the proportions are the same for all 3 treatments, that's stating that this is true, there is a 7.96% chance of getting a difference as large or more extreme than our sample, would be the p-value. Okay, what conclusion can we draw from this? Well, clearly we see that our p is greater than alpha in this case. Because of that, we cannot reject H sub O, and we cannot conclude H sub A. We'll put that in context. That means what we cannot conclude is we cannot say that there is at least some difference in the proportions. Number 13, in the United States, there's a strong relationship between education and smoking. Well-educated people are less likely to smoke. Does a similar relationship hold in France? To find out, researchers recorded the level of education and smoking status of a random sample of 459 French men aged 20 to 60 years old. The two-way table displays the data. So here we've got it. Is the relationship between smoking status and education level statistically significant? Given appropriate evidence to support your answer. You guys, this is a state plan do conclude test. So we're going to start off and determine which type of chi-square test is this. Well, what you're seeing here is they took one sample and they are measuring two variables. They are measuring education and smoking status. So one sample, two variables, is going to be the test for independence or association. You can choose to state your hypothesis using either one of those. I'm going to go ahead and talk about it in terms of independence. So let me start by stating the hypothesis, and I'm going to say H sub O is that education and smoking is independent. I'm just going to abbreviate here. Smoking is independent. But we really don't think that's true. We think H sub A is the case. We think that there is some dependency. So education and smoking has some dependency. Now you can state it that way, or you could do association. If you said association, you would say for hypothesis that's null. There is no association between these variables. Or H sub A, there is an association between the two variables. Let's choose an alpha of 0.05, and let's write out that we are doing the chi-square. And I did for mine a test of independence. And that will cover us for the state and part of our plan. And you should spell out independence, by the way. Okay, for the plan, let's go ahead and check for randomness. So on here, if we take a look at it, it clearly says there was a random sample, so write that there was a random sample taken. Independence, can we assume that there are at least 4,590 Frenchmen? Yes, we can. So between the ages of 20 and 60, you could write that down. For expected counts, so we can use chi-square, we do have to find all the expected counts. Are they at least 5 or higher? So what I would do in this case, you can write expected counts are greater than or equal to 5. You must show that you have all the expected counts. Either go back to the table and write all of the 12 expected counts or list them somewhere down here. Where I would get them from personally is I would go ahead and run the test for independence on the calculator in matrix A, go back to matrix B, and just write them all down. Just so you can double check some of your numbers, I'm going to write down the first three for the first column. I had 59.4 for the first cell, 44.2 for this second. The third one is 42.3, and that is just for the non-smoker group. You're going to want to show it for the other 9 cells here. Remember to compute it by hand. It would be row total times column total over the total of everyone in the table. So that is over 459. All right, I'm going to move into the do portion now. So for the do portion, after you have run the test, all I would suggest writing down for do is let's write down the chi-square statistic. It's 13.304. The p-value was 0.0384. The degrees of freedom must be listed. It's going to be rows minus 1 times columns minus 1. So that's going to be 3 minus 1 and 4 minus 1, which is going to give us 6 degrees of freedom. So we have our answer. Now let's make our conclusion. So for the conclusion, what I could say, in this case, P is less than alpha. So let's show that value is less than 0.05. We can reject H sub O. And instead of just saying conclude H sub A, I'm just going to say and conclude that there is some dependency between education and smoking. Moves us on to part B. Which cell on the table contributes most to the relationship? If you go into here You want to actually go back to all 12 elements that you see in this table here, all 12 pieces, and see whose chi-square contribution was the largest. But we don't expect you to sit here and compute the chi-square contribution, which is the 13.3 in theory is split up and made up of all 12 of these boxes. It makes up a piece of that 13. What I would do is just look at the observed minus the expected value difference. And the ones where you're going to see the largest difference, there are two cells in particular. I'm going to jot down for heavy university was 24.37. The two cells that should pop out the most here are going to be the university non-smoker difference and the heavy university difference in here. So if you look at it, those that have the larger chi-square contribution is going to be, again, the heavy users at the university and the non-smokers at the university. What this is showing us is that our study showed us we had 53 non-smokers at the university, but in theory we would have expected 42.3. In our study we had 16 heavy smokers, but we would have expected more. So we're actually seeing more non-smokers than we had expected and fewer heavy smokers in those two categories. And that kind of makes up the analysis.